Before we talk more about the y86 semantics, let's think about this question for a second. So here's an instruction in y86, IR-move-q 128 RSP. So think about this for a second and see if you can identify the best answer here. And then pause the video. Okay, so you might be tempted to pick A here. It's a pretty straightforward description of what this instruction does, and it's probably the meaning that we're most interested in as a y86 programmer. As a y86 CPU architecture implementer, however, you should be more concerned about a precise description of what effect this instruction has on the machine. And so a better answer here would be C. It sets RSP to 128 and it increments the PC by 10. This is a more complete description of what this instruction does. So hopefully this motivates a little bit what we're doing here. So we've already defined semantics of a y86 instruction as the effect that it has on a y86 machine. And at this point, we really need to specify these semantics very, very formally. And this will help us think about P4. The more formally and more mathematically we can express these semantics about what an instruction does, the closer it's going to be to the code that we'll need to write in Project 4 in order to emulate a y86 CPU. So the ISA reference sheet, as I mentioned before, the y86 reference sheet includes these mathematical semantics. So those are these things at the bottom. I gave you a brief overview before. There are some syntax notes that I should make here. So when we use this syntax here, so R sub RSP, this means the value of the RSP register. When we say something like R sub RA, this means the value of the register with the register ID RA. We'll use, so basically R with indexing means read from a register or write to a register. An M with the brackets means read or write from memory, and we'll use a subscript to indicate how many bytes we're going to read or write. So M sub 1 means 1 byte of memory, M sub 8 means 8 bytes of memory, and we'll put the address inside of the brackets. So M sub 1 of PC means the value of 1 byte in memory at address PC. M sub 8 of PC plus 2 is the value of 8 bytes in memory at address PC plus 2. We'll use the colon notation where we need to separate a byte into its low order and high order 4 bits. So RA colon RB equals M sub 1 of PC plus 1 means let's go and read the byte in memory at address PC plus 1, and then we're going to split it into the high and the low order 4 bits. The high order 4 bits are going to be RA, the low order bits are going to be RB. We're also going to have this COND or condition function, which takes the condition codes and the current instructions function, the ifun, and it returns a 1 or a 0 based on those things. Basically, this is determining whether or not the given CMove or conditional jump should happen. And there are some tables in your textbook that will help you implement this function when you get to Project 4. We're going to ignore the details of that function for now and just assume that we can look at the condition codes and the ifun to determine whether or not we're going to take a particular jump or do a particular conditional move. We're also going to have a couple conventions here. We're going to write addresses using hexadecimal. We're going to pad them to 3 characters, and we're going to write integer literals using decimal with no padding. All right, so let's work through an example. So here is that example that we saw before. So the IR-move-q 128 RSP. And so this is the address of this instruction in memory, and here are the bytes of the instruction. These are little endians, so this is the first byte, and then this is the second byte, and third byte, and so forth. All right, so let's look at the semantics here and work through it line by line, stage by stage. So we'll start in the fetch stage. So this first line is icode colon ifun gets the value M1 of PC or sub PC. So this means that we're going to read a byte from memory. The address that we read from is going to be PC. Right now, the program counter is presumably pointing at this instruction, so the program counter value is going to be 016. We're going to read in that byte, so that's going to be this 30 value here in hex. And we're going to split it into the high order 4 bits, which is going to be this 3, and the low order bits, which is this 0. We're going to do the same thing with the next byte. So the PC plus 1, that's going to give us F4. And we're going to split that into the high and low order 4 bits. So RA will get the F, and RB will get the 4. Then we're going to read in 8 bytes for the literal value. So that's going to be the remainder of these bytes. And so we'll have to figure out what that value is. And if you kind of work it out, you'll see that it's the 128 that we had here. And so we're going to take that value, we're going to store it as, or we're going to save it temporarily in our CPU as val-c. We're also going to take that program counter, we're going to add 10 to it because this was a 10-byte instruction. And so we'll have the address of the next instruction, which is val-p, will be, whatever this value is, plus 10. So this is how we're going to work through these things in the lab for today. So you'll have these semantics on the Y86 semantics sheet. And what we're going to ask you to do is to fill out the actual values for a particular instruction as it's executing in the CPU. So we've already talked through these things, but here they are sort of formally written down. So the ICode ifun is given the value of M1 of PC. We know the value for PC, so we can go ahead and fill that in. And we know what this value is going to be because we have it right here. So we can go ahead and write that down, and we'll go ahead and separate it because we know that we're going to be separating it. So now we know that the ICode is 3 and the ifun is 0. Same thing on this next line, except we're reading from PC plus 1 instead of PC. So that's going to be reading from this location. And again, we're going to split it. So we know that RA is F, which means we don't have an RA, right? We only need one register here, and that's going to be our destination register, which is 4, which if we go and we look up our register IDs, we'll see that that corresponds to this RSP. The constant value that we get out of our instruction is going to be the rest of these bytes. And so again, if you were to work this out in from hexadecimal to decimal, then you'll see the value is 128. So that's our val-c. And then we do the addition here, and we see that this is the new value, or this will be the new value of the program counter when we're done executing this instruction. All right, so at this point, I would encourage you to pause the video and see if you can work out the rest of this, and then we'll talk through it after you finish doing it yourself. Okay, so here's what you should have arrived at. So nothing happens during the decode phase, so we don't need to write down any concrete semantics there. During the execute phase, we are going to be taking the value of val-c and sort of adding an implicit 0 to it. So this is not actually, this is doing an arithmetic operation, but it's not really one that we really care about that much. So we'll just, copy the value that we had for val-c into val-e. So val-e is now 128 as well. This instruction doesn't read or write memory, so there's nothing during that phase of the CPU. We get to the write back phase where we see that we take the value that we had for val-e, which is 128, and we save that into R of RB. So we know that that is going to be RSP. So RB we figured out up here is 4, which corresponds to RSP. So R of RSP is given the value val-e, which is 128. So that's going to set the register. Which is the first effect that we care about. This is the first effect that is visible to the next instruction, right? This will be saved in the register file. The other change that's going to be visible after we finish executing this instruction is, of course, the PC update. So here we've taken the value that we calculated as the address of the next instruction, which is val-p, and we're going to save that in the program counter. So that's going to be 0x020. And so now we can see that the effects that are visible outside of this instruction are that we set RSP to 128 and we increment the program counter by 10.